Hi guys, and welcome to this Set A Paper 2 exam walkthrough. So as I mentioned for the first paper, so that was Set A Paper 1, this is a paper that I put together myself with all questions written by me. Now there will obviously be some inspiration from previous past papers, so some of the questions might look fairly similar, but they should still hopefully give you some good practice. Now if you are using this paper as a 2023 student, and using this almost like a predicted paper, then just be aware that I wrote this paper before the official Edexcel paper the other day. And for that reason, some topics do appear in this paper that were on paper 1 for Edexcel. It's not a perfect match in terms of topics, but either way, you should still hopefully find this as useful revision. So I think that covers everything. If you're still looking for extra A-level maths revision, then be sure to check out AJMaths.co.uk. We have worksheets, revision videos, and all our predicted papers can be found on our website as well. So other than that, good luck for your upcoming exams, and thanks for watching. Starting off then with question 1 here on paper 2, we're given that y can be expressed in terms of x as y equals 1 over 4 x to the power of 5. Now we're asked to express the following in the form ax to the power of b, where a and b are constants to be found. Let's begin here with part A. So for part A then we have y squared. If y is equal to 1 over 4 x to the power of 5, that's y, so if we want y squared, we're simply going to square both sides here. In that case, we have 1 over 4 x to the power of 5. We're squaring both sides here. Well, this is just simply 1 over 4 x to the power of 5 times by itself again. So 1 over 4 times by 1 over 4, that would give me 1 over 16. Get 1 over 16 there. And then x to the power of 5 here, so I've got a power raised to another power. So we just multiply the powers together then. We've got 1 over 16 x to the power of 10. 5 times 2 gives me 10 there. That's a solution to A. Moving on to B now, so we have y to the power of minus 1. So just using the rule for indices here, this is the same as 1 over y. So 1 over y here. So using this expression here, this is the same as 1 over 4 x to the power of 5 there. Now if it helps here, what I'm going to do, I'm going to write this as 1 over x to the power of 5, x to the power of 5 all over 4, like so. And then from here, what I've got now is this number here, 1 divided by this fraction. I've got 1 divided by x to the power of 5 over 4. So just using the rule here for dividing by fractions, this is the same then as 1 times 4 over x to the power of 5. If I change this to 1 over 1, I'm simply going to get 4 over x to the power of 5. And then just making sure we use the rule of indices here, because we want it in the form ax to the power of b. This is the same then as 4x to the power of minus 5. Okay, so that's a solution to B. And then finally, let's do C underneath here. We've got the square root of 4y. What I'm going to do here is I'm going to times y by 4. So 4y here, that would be 4 times 1 over 4 x to the power of 5. That would simply leave me there with x to the power of 5. In that case then, the square root of 4y, well that would simply be the square root then of x to the power of 5. And if you take the square root, that's the same as taking the power of a half, or raising it to the power of a half I should say. You've got x to the power of 5 here, x to the power of 5, that's all raised to the power of a half there. Okay, and again just using the power rule here, so we've got a power raised to another power, we simply multiply the powers together. So in that case then, this gives us x to the power of 5 over 2 there. Okay, so x to the power of 5 over 2, and there we have it. So that's the solution to C, and the solution to question 1. Moving on to question 2 here then. So we've got figure 1 above, which shows a sketch of the curve C with this equation here. We're then told that the finite region R shown shaded in figure 1 is bounded by the curve C, the x-axis, the line with equation x equals 1, and the line with equation x equals 3. What we've also got here is this table. So this table shows corresponding values of x and y for this given equation here. So for the first mark here then, just one mark to get us started. For part A, we're simply looking to complete this table above, giving the missing values to 3 decimal places. So nice and straightforward here. All we're going to do is substitute x equals 1.5 into this equation. Do the same then with x equals 2.5. So when x equals 1.5 here, in this case then, y would be equal to 1 over, it would be the square root of 1.5 plus 1, so it would be the square root of 2.5. Obviously just put this into your calculator here, just make sure that you give your answer here to 3 decimal places. If you do this correctly here, you should get 0.632. This value here. Just doing the same now with x equals 2.5. We do that underneath. When x equals 2.5 then, y is equal to 1 over the square root. In this case now it would be 2.5 plus 1, giving us the square root of 3.5. And that would be equal then, again, just putting this into your calculator, just make sure you give the answer to 3 decimal places. In this case here I get 0.535. Okay, that's this value here, 0.535 there. Okay, so we complete the table. I guess is the first mark there, so that's part A done. Let's take a look now at part B here. So for part B then, we're simply using the trapezium rule now, using all the values of y in the table to obtain an estimate for the area of the shaded region R, giving our answer to 2 decimal places. So just remember here, the formula for the trapezium rule is given in the formula book, so you don't have to worry about memorizing this result. So let's just start by stating the result here. So we've got the integral here of y dx from A to B. And the area here is given approximately by 1/2 times by h, or h over 2, whichever way you prefer to write that. Then we've got the first result, so y0, plus the last result, yn. Now we've got 2 lots of everything else, so I've got 2 lots of y1 plus y2, and that's all the way up to yn minus 1. Okay, that would be our penultimate value there in our table. We've got enough room there. So if we put all that together then, so h, don't forget that's also given in the formula, but h would be equal to b minus a divided by n. Now, in this case here, you don't actually need to go and find h. Remember, h is the width of the interval. But in this case here, h in our question here would be 0.5. We're increasing by 0.5 each time. Okay, so for our question here, h is 0.5. If we put all this together here then, the area then would be approximately 1/2 times h. So if h is 0.5 or 1/2, we've got 1/2 times by 1/2 again. And we times all this here. So it's the first term and we add the last term together. So I've got 0.707 plus 2. Now I've got 2 lots of everything else. So I might run out of room a little bit here. Let's see if we can fit all this on. We've got 0.632. We've then got 0.577. Then we do the next one underneath here. I've got 0.535 there. Okay. Obviously, all I need to do now is just put all of this here into my calculator. So do this correctly here. Obviously, this would be 1 over 4, a quarter, times by all of this here. So again, just put this into your calculator. And we're giving our answer now to 2 decimal places. So what I get then for the area here, that the area is approximately 1.55 there. Okay, and that's to 2 decimal places. Okay. There have it. So that's the solution to B there. And then finally for part C here, it just says, briefly explain how the trapezium rule can be used to obtain a more accurate estimate for the area of the shaded region R. So just one mark here, we simply need one comment to get us that mark. And all you're looking for here is basically we just need to increase a number of strips here to obtain a better estimate. So all I'm going to say here is increase the number of strips. Increase the number of strips to obtain better estimate. Okay, and there we have it. So anything to that kind of degree, just basically a comment regarding the number of strips. We want to increase the number of strips to get a better estimate, okay, or a more accurate estimate there. Okay, and there we have it. So that's the solution to C, and that gives the solution there to question 2. Take a look now at question 3 here. So we've got 2 parts. Let's begin with part A then. So part A is a proof by exhaustion. So it says prove by exhaustion that a squared minus 2 is not divisible by 6, where a belongs to the integers here, and then a is between 3 and 6. So with a proof by exhaustion, remember, all we need to do here is simply exhaust all the possible cases. So in this case here, the options that we need to exhaust here would be a equals 3, 4, 5, and 6. So when a equals 3 to begin with, so when a is 3, what we get here is we get 3 squared minus 2. So 3 squared is 9 minus the 2. That would give me 7. So now we just check whether this is divisible by 6. Well, clearly 7 is not divisible by 6. 7 not divisible by 6. And therefore it fails in that case. So it fails for a equals 3. So now let's keep going through the possible cases here. So we have a equals 4. In that case, we get 4 squared minus 2, so that's 16, minus 2, so that gives us 14. Again, in this case here, 14 is not divisible by 6. Not divisible by 6. So therefore it fails when a equals 4. Testing a equals 5 now. In this case, we get 5 squared minus 2, so that's 25. Minus 2, giving us 23 there. Again, checking whether this is now divisible by 6. Well, 23 is not divisible by 6. In that case, it fails for a equals 5. And then finally, we arrive at the last possible case here. That's when a equals 6. And in this case here, we get 6 squared, so that's 36, minus the 2, giving us 34 there. And in this case here, again, just checking whether this is now divisible by 6. Well, 34 is not divisible by 6. So therefore, it fails for a equals 6. So therefore, what we've proven here is by exhaustion that a squared minus 2 is not divisible by 6 when a is an integer and a is between 3 and 6. Let's just make a quick conclusion here just to finish this proof. So therefore, a squared minus 2 is not divisible by 6 where a belongs to the integers and a is between 3 and 6. Let me try that again. Okay, we've done this here by exhaustion, so by exhaustion there. And we don't really need anything else, so we've proved each possible case. A equals 3, a equals 4, a equals 5, and then finally a equals 6. Okay, so there we have it. So that's the solution to part A. That's the proof by exhaustion complete. Let's just clear the screen here to have a go now at part B. With part B then, it says use proof by contradiction to show that there exist no integers x and y such that ax plus 20y is equal to 3. So where do we begin here? Well, for a proof by contradiction, we need an assumption to begin with. So for part B then, what I am going to do now is assume that there do exist integers x and y. So assume there does exist. So hopefully you can read my writing. I know it's not the neatest. So assume that there does exist x and y such that. And we have this here, so ax plus 20y is equal to 3. Okay, basically what this is saying is 8 lots of an integer plus 20 lots of an integer is equal to an integer. Okay, so in other words, integer is equal to another integer. But what we need to do is show that there exists no integers x and y such that this equation here holds. Okay, so we've got our assumption here to begin with. So basically what we need to do is kind of work through this now and arrive at a contradiction, giving us the proof by contradiction. Okay, sounds a bit obvious, but that's what we're aiming to do. So what I'm going to do to begin with here, if I just take a look at this equation here, the only thing that I can really do here is work with the left-hand side. And in that case, all I'm going to do then is factor out what I can here. So I can factor out the 4 here. I'm going to get 4 lots of 2x plus 5y. And that is equal to 3. Okay. And from here, the only other thing that we can really do now is to divide both sides by 4. Okay, there's 4 here. In that case, then we get 2x plus 5y is equal to 3 over 4. Okay, so just dividing both sides by 4 here, we get 2x plus 5y equals 3/4. And at this point here now, we arrive at a bit of an issue. And I'll give you a moment just to think about why this is an issue. And hopefully you can spot why this is the issue here. So the issue that I arrive at now is because we did assume that there exist x and y. I should have stated here that these are integers. So x and y, let me just write underneath, x and y belong to the integers here. So that's kind of the important point here. If we forget that, it's not much of a proof. So x and y belong to the integers. So if x and y are integers, then obviously if I times it by 2, it would still be an integer. Then again here, if y is an integer, if I times it by 5, that still remains an integer. So in that case then, I'm going to do it over here. If x and y belong to the integers, okay, so if they belong to the integers, in that case, 2x and 5y also belong to the integers. Now you can do this kind of in words. I'm kind of doing it shorthand, just using mathematical notation. I'm doing it just to kind of save me a little bit of room and a little bit of time here. But basically all I'm saying here is if x and y belong to the integers, then in that case, 2x and 5y must also be integers. Okay, so in that case then, what I've got here now is an integer. So therefore, an integer plus an integer, you should be aware that that would give us an integer. Okay, so an integer plus an integer should be an integer. But what I get here is 3 over 4, which is not an integer. So integer plus integer cannot be equal to 3 over 4. So therefore, we now arrive at our contradiction here. Let's do my conclusion up here. So therefore, this contradicts our original assumption. This contradicts our original assumption. So in other words, the assumption must be false. The assumption must be false. The assumption must be false. And therefore, just to finish here, we say, basically, there exist no integers x and y such that ax plus 20y is equal to 3. Let me just write that down in full. There exist no integers x and y such that, and then we have the original equation. So ax plus 20y is equal to 3 there. Okay, and there we have it. So I know the kind of conclusion here is a little bit lengthy, but it is important that we do give that conclusion there just to finish the proof. Okay, so hopefully that makes sense. So we had our original assumption here. We then work with this equation, factoring the 4 out, dividing both sides by 4 here. So this must be an integer, this must be an integer, but clearly if we have an integer plus an integer, we can't get 3 over 4. That gives our contradiction there, and therefore the assumption must be false, and then basically it proves the original concept here. Okay, but there we have it. So that's the solution to B and the solution to question 3. Taking a look now at question 4 here, we've been given figure 2, and figure 2 shows a sketch of the curve C with equation y equals f of x. So we can see f of x here below. And we're also told that the point P with x1, little p, is a stationary point on the curve. We can see that here on the diagram. And we're also told that the equation f of x equals 0 has one real root of alpha. And again, we can see that here on the diagram. So for the first part here, part A, we're simply asked to show that alpha lies between 1.6 and 1.8. So to do this here, what we're going to do is show a change of sign. So if we consider these two values here, so f of 1.6 and f of 1.8. Obviously what we'd expect here then, let's say this is 1.6. Obviously we'd expect a negative value there. And let's say this is 1.8 here. Then we'd expect a positive value there. Okay. So obviously in that case then we can show one is negative, one is positive. And our function here, f of x, is continuous. Then in that case, alpha must lie between these two values here. Okay, that must mean there's a root here in this interval. So let's just consider now these two values here. What you're simply doing here is substitution. So substitute x here equals 1.6 into this function. What you're going to get here then is 1.6 squared minus 1.6 minus the square root of 1.6. If you do this correctly here, what you should get then, minus 0.3049 and so on. Okay, so that's fine. We don't need all the digits here, but just to show that this value here is negative. So then for f of 1.8 here, again, just substituting 1.8 now into this function here. And again, what you should get here then, as long as you do this correctly, you get 0.09835 there. Okay. So in this case here, like we predicted here with our diagram, one of these values is negative. So this value here of f of 1.6 is negative. So f of 1.6 less than 0. F of 1.8 then is greater than 0. It's positive. So f of 1.8 really greater than 0. So therefore what we have here is a change of sign. So we have a change of sign. Now our function here, f of x, is continuous. And f of x is continuous. I'm not very good with spelling, so probably misspelled that, but let's just go with it. So f of x is continuous, so therefore what we can say then is alpha lies in this interval. Okay. And there we have it. So that's all we need to do there for part A. So that gets us the first 2 marks. So for B then, it says briefly explain why x0 equals p should not be chosen as a first approximation to alpha when using the Newton-Raphson method to f of x. So why is there an issue with this point here? Okay. So just think about how the Newton-Raphson method works here. So what you do is you draw a tangent line from this point. Okay. Now clearly if I draw a tangent line from this point, if this point here is a stationary point, then my tangent line here is just going to be a horizontal line. Okay. I'm not using a ruler here, so it won't be perfect, but obviously you get something that looks like this, right? So clearly this line here, it's a horizontal line. It's not going to intersect here with the x-axis. Okay. So for that reason, the Newton-Raphson method will fail. The other way you could think about this as well is considering what happens here with the derivative. So if we just write down the formula here for the Newton-Raphson method, I've got xn plus 1 is equal to xn minus f of xn all over f prime of xn. Okay, so clearly f prime of xn, so f prime at this point here, that would be 0. So I'd be dividing by 0, and clearly we can't do that. That would cause an error. So there's 2 reasons there that you can state. Either of those reasons is absolutely fine. So basically, all I'm going to say here is P is a stationary point. So P is a stationary point. So tangent line is horizontal. And won't intersect with the x-axis. Okay, won't intersect the x-axis. Therefore, Newton-Raphson method will fail. That's absolutely fine there, that would get you the mark. But like I said, you could also mention the fact that f prime at this point here, again, that would be 0, and obviously we can't divide by 0. So either of those reasons there is absolutely fine. It is only 1 mark, so again, not too much work there. Okay, that's part B done. So now we arrive at part C here. So let's just clear the screen here to have a go at part C then. So for C now, it says using x not equals 1.6 as a first approximation, apply the Newton-Raphson method to f of x to obtain a second approximation. So let's just recall the formula then for the Newton-Raphson method. Don't forget this is given in the formula book, but I'm just going to write it down here just so we've got it on the screen. We've got x of m plus 1. That is equal to xm minus f of xm. That's all divided by f prime of xm. So if x naught here is 1.6, then what I'm going to do here to begin with is also find f prime of x. So I'm going to differentiate f of x here, so f prime of x. What would that give us? So just differentiate term by term here. So x squared, that would give me 2x. Minus x here, that would give me minus 1. Now for the minus the square root of x here, what I'm going to do then is write that as minus x to the power of a half. When you differentiate this here, we're going to get minus a half x, and we reduce the power by 1. I'm going to get minus x, a half x. I'm struggling to differentiate this simple term here, so minus a half x, the power of minus a half, there we go. And if it helps, rewrite this here, so this is 2x minus 1. I can write this then as minus 1 over 2 lots of the square root of x, okay? And I'd leave it like that because obviously we need to use substitution here a little bit later on to evaluate f prime of 1.6. So I would write it in this form here. It's this second form there. We've got everything that we need now, so let's find our second approximation here. So x1 here, that's going to be equal to xn, so that would be x0, so 1.6. So we've now got f of 1.6 here, which we technically evaluated in part A when we're showing the change of sign. And what I'll do is I'll just write them underneath here. So do them at the bottom. So f of 1.6. If I write it in full here, I get minus 0.3049110641. And what I would do here is use all the digits here just to ensure that we have full accuracy. So that's f of 1.6. And I also need f prime of 1.6 here. We're now using this here, just substituting 1.6 here for x. So in that case then, if we do this correctly, what you should get is 1.804715,292. Okay. So we've got everything that we need then. So 1.6 minus, so f of 1.6 will be minus 0.304 and so on. 9110641. I know it is quite tedious when you use all digits, but do ensure that we have full accuracy here. Then f prime of 1.6, that's going to be 1.804715,292 there. Then all you need to do here is just put all of this now into your calculator here. If you do this correctly, then for x1, what you should get here, just giving your answer to 3 decimal places, is 1.769 there. Okay, and there we have it. So that's our second approximation there. We're just using the Newton-Raphson method once there. Yeah, our second approximation, and there we have it. So that's the solution to C, and that gives the solution there to question 4. Taking a look now at question 5 here, we've been given the curve C, which has equation of y squared minus x, which is equal to 3xy plus 2. We want to show that dy by dx is equal to 1 plus 3y all over 2y minus 3x. So quite a nice question here, so we just need to find dy by dx. But to obtain dy by dx here, we need to use implicit differentiation. So we're going to go term by term here. Obviously, anything that's just in terms of x only, that's nice and straightforward to differentiate. However, anything that's just involving the y here, so for example the y squared and the 3xy here, a little bit more complicated. So for the y squared then, what I say here to begin with is just imagine that's x squared. If you were to differentiate x squared, you'd get 2x. So same here, with it being y squared now, that would give me 2y. But what I need to do here is multiply this result by dy by dx. So for the first term here, the y squared, we get the 2y like we mentioned. Like we said, we now multiply this here by dy by dx. Like so. For the minus x here, just differentiating that with respect to x, that would simply give me minus 1 there. Now for the 3xy, again, a little bit more complicated here. And to actually differentiate this, we need to think about the product rule now. So I'd say u here as being the 3x, and v as being y here. If I obtain u prime here, so just differentiate 3x with respect to x, that would simply give me 3. Do the same here now with v prime, or v here, so if you differentiate v here with respect to x, because that's y, well, if that was just x, you differentiate that, you get 1. So that would give me 1 here, but don't forget we now need to multiply this by dy by dx, so I just simply get 1 times dy by dx, giving me dy by dx there. Okay? So in this case now, applying the product rule here, I get u times v prime. I get 3x times dy by dx. So 3x times dy by dx. And then we have u prime times v. So I get 3y there. So plus 3y. And then for the 2 here, well, that's a constant. If you differentiate that, that would become 0. Okay? So what I need to do here now is rearrange and make dy by dx the subject. So we've got multiple dy by dx's here. I've got one here on the left-hand side and one here on the right-hand side. Let's just get those on one side only. If I take this 3x dy by dx over onto the left-hand side now, I'm also going to add 1 to both sides here to get rid of this minus 1 on the left-hand side as well. What I'm going to get here is 2y dy by dx minus 3x dy by dx is equal to 1 plus 3y. Like we said, all I've done here is I've added 1 to both sides and subtracted 3x dy by dx off both sides. So now what I'm going to do here is I'm going to factor the dy by dx out. We get dy by dx. I get 2y minus 3x. And that's all equal to 1 plus 3y. And we're nearly done here now. We just simply want dy by dx. So to get dy by dx here, I'm just going to divide both sides by 2y minus 3x. So therefore, dy by dx is simply 1 plus 3y all over 2y minus 3x. And that is just what we need here, so as required. Okay, and then so that's dy by dx there, and that gives the solution to question 5. If we take a look now at question 6 here, we're asked to prove that if x minus q is a factor of f of x, then f of q is equal to 0. Where do we begin here for part A? Well, to begin with, let's consider f of x. So f of x here, well, if x minus q is a factor, then we can write f of x here as x minus q times by g of x, where g of x is just some polynomial. Okay, I've got this factor here. So now let's consider here then what we have with f of q. So f of q here, so just replacing any x now with q, we get q minus q there, times by g of q. Okay, well clearly q minus q would be 0, so f of q here equal to 0 times g of q. Now we say anything times by 0 is equal to 0. So therefore, f of q is equal to 0 as required. Okay. That's part A done. Hopefully pretty nice and straightforward there. Just the 2 marks there for the proof. So that's part A done. So let's take a look now at part B here. So for part B then we've been given this function here, f of x. So let's just clear the screen. We've got enough room for part B. We've been given f of x here. It says hence show that x minus 2 is a factor of f of x, and that f of x can be expressed in this form here, where q of x is a quadratic expression to be found. Where do we begin here? Well, we're just using the factor theorem here. In this case, if x minus 2 is a factor, then what we know by the factor theorem is f of 2 should be equal to 0. Okay, that's what we're looking to show here. So in that case then, f of 2, we'll just substitute 2 now into this function here. So I get 2 lots, 2 cubed. I then got minus 5 lots of 2 squared. We then got 12 lots of 2. And then minus 20. Okay. So if we evaluate this here, 2 cubed is 8, times that by 2 gives me 16. 2 squared is 4, times that by minus 5 gives me minus 20. 12 times 2 is 24. And then finally, minus 20. Well, 16 plus 24 is 40. Minus 20 gives me 20. And minus another 20 there gives us 0. Okay. So therefore, x minus 2 is a factor. X minus 2 is a factor of f of x. So that's the first part done there for B. What we also need to do now is show that f of x can be expressed in this form here. So q of x is a quadratic expression to be found. Let's just write this down here. So f of x, that is equal to, that's supposed to be a bracket there, believe it or not. This is x minus 2 times by a quadratic expression. So if I just take a general quadratic here of ax squared plus bx plus c. Okay. Now there's a couple of different ways you can actually do this part here. One way to do this would be to use algebraic long division. That would be one way to do it, using obviously f of x here and this divisor of x minus 2. That would be one way. The way that I'm going to do it though is using inspection. Okay. So we can derive this quadratic here by using inspection with this factor here and the actual function that we know we need to obtain. Okay. What do I mean by that? Well, for example here, if we think about this for a moment, so this should be equal then to 2x cubed minus 5x squared plus 12x minus 20. Okay, that's what we need to obtain here. So for example, I know that this number here, this minus 2, times by this constant here at the end, this c, that should give me minus 20. Okay, that's the only way we can get minus 20. So from there, I can obtain the value of c because I know minus 2 times by c is equal to minus 20. In that case, then c is equal to minus 20 divided by minus 2, and that would give us positive 10 there. Okay, so now I know that f of x here can be expressed so far as x minus 2 times ax squared plus bx plus 10. Okay, so we found the value of c there. We now need a and b. So a and b are a little bit more complicated, but nothing too crazy. So for a then, so I've got ax squared. So I know that I need to get 2x cubed here. So the only way that I can get 2x cubed is by taking this x here and timing it by ax squared. Okay, so x times ax squared would give me ax cubed. And then by comparing the coefficients here, so ax cubed should be equal to 2x cubed. We can see then that a must be equal to 2. Okay, so a is equal to 2. So in this case now we've got x minus 2 times 2x squared there plus bx plus 10. Okay, let's box this off over here. And finally then, we just need b now. So again, we just need to think about how we can obtain this. So what ways can we obtain the b term here? Well, think about comparing here. So let me just think about this for a moment. So I know that I can get the 10x here. So x times by the 10 would give me 10x. Okay, so I've got 10x there. What other way can I get the x term on its own? Well, that would be this minus 2 here times by bx. Okay, that would give me minus 2bx. Okay, so we know then that we should get 12x here. So comparing the coefficients now, 10x minus 2bx should be equal to 12x. Okay, so in that case then, if we solve this here, I can subtract 10x off both sides. I've got minus 2bx equal to 2x, so subtracting 10x off both sides. And then finally, we just want b here on its own. Therefore, b is going to be equal to 2x divided by minus 2x, which in this case would give me minus 1. Okay, so there we have it. So if I just put all this together then, we get x minus 2 times 2x squared minus x now, because b is minus 1, so minus x there, and then plus 10. So hopefully the last bit made sense here. So all I've done then is matched up the x part here with what I can match from this expression here. The only way to get terms in terms of x only would be minus 2 times, the 10 times the x here, so x times 10 gives you the 10x, then the minus 2 times the bx here. That's the only way we can get just x on its own. But then we can compare that to 12x, which we know we need to get. Solve them for b, and you get minus 1. Okay, that's what you should get there for b. So that's your final part there. And then finally for c here, it says hence or otherwise show that the equation f of x equals 0 has only one real solution. So let's just clear the screen here to have a go at c then. So for c now, if f of x equals 0 here, so if we go back to this form here that we just got, so let me just write that down. Start with, we have x minus 2. We got, what did we get? We got 2x squared minus x plus 10 there. So we know we have one solution here. So this is equal to 0. I have one solution here of x equals 2. Then we need to consider these solutions here to this quadratic. Okay. Now my suspicion here is, if we only have one real solution, it would be this solution here. Obviously we know that solution is x equals 2. So this clearly here, this quadratic has no solutions. In that case, what we'd expect to show then is the discriminant here of this quadratic is less than 0. Okay, so let's consider the discriminant now. I'll consider delta here for the discriminant. So in this case here, the discriminant then, just remember the discriminant is b squared minus 4ac. What I've got here then is minus 1 squared. Minus 1 squared minus 4 lots of ac, so minus 4 times a, which is 2, times by c, which is 10. In this case here, minus 1 squared is 1, minus 4 times 2 is 8, times by 10 there, that gives me 80. So 1 minus 80 there would give me minus 79 there. Okay, so let me just double check I've done everything correct. So using the discriminant, b squared minus 4ac. b here is minus 1 all squared, so that gives you 1 minus 4ac, so 4 times a, which is 2, times that by c here, which is 10. Yeah, perfect. So we get 4 times 2, which is 8, times it by 10. We get 80 there. The discriminant here, minus 79. The discriminant then is less than 0. So therefore, 2x squared minus x plus 10 has no real solutions. Okay. So therefore, the only real solution here then is x minus 2. So therefore, f of x equals 0 has only one real solution. Okay. Run out of room a little bit, but that should do there. So, like we said, for part C then, we're just considering the discriminant here. Show that the discriminant is less than 0, so therefore that quadratic has no real solutions. And in that case then, f of x equals 0 has only one real solution. Okay? And there we have it. So that's the solution there to question 6. Moving on to question 7 here. So it says figure 3 below shows a graph of the curve y equals x to the power of 4 plus bx to the power of 3 plus cx squared plus dx plus 6, where b, c and d are all real numbers. And we can see figure 3 here showing the quartic. So underneath it says the student prepares to answer a question based on this quartic expression, however their pen leaks and drops a small circular blob of ink covering the final root. We can see that here this little blob just covers the final root. It also says the point Q, so that's this point here, meets the y-axis with y-coordinate 6. So point here Q has coordinates of 0, 6. Okay. So for the first part here, part A, it says determine the final root. So how do we answer part A here? Well, we need to use this sketch here to answer part A. So we can see 3 of the 4 roots here. So I can see that we have 4 roots. So I've got one root here, got one root here, one root here, and I've got this final root here. Okay. So in that case then, if we have 4 roots like this, we can express it as a product of 4 linear factors. So 4 roots, that tells us we can express this here as a product of 4 linear factors. So let me just write this down to begin with. Right, so the product of 4 linear factors. Now, if you think about how this sketch works here and how this curve works, your y-coordinate here for this point here, so the point Q, where it meets the y-axis here, that y-coordinate is the product of these roots here. So minus 2 times minus 1 times this number here would give us this y-coordinate. So in other words, minus 2 times minus 1 times 1 and times this number here, which we don't know, but we know obviously it must be positive. But in that case, if I just call it A here, it don't really matter what I call it, but if I call it A, that must be equal to the y-coordinate of this point here, Q, which is 6. So I'm going to set this equal to 6 here. So in this case, if we just evaluate this left-hand side here, minus 2 times minus 1 is positive 2. Times that by 1, I still get 2. Times that by A, I get 2A. Is equal to 6. So in that case then, dividing both sides by 2, I get A equals 3. But in this case here, the number, the root underneath this blob of ink here, that would be 3. So at this point here, that root is 3. Okay. That's part A done, first 2 marks there. So for B now, it says hence or otherwise find the value of B, C and D. So B, C and D are in the quartic here. So how do we find these values? Well, like we said, we have 4 roots, so I can express this here as a product of 4 linear factors. And now we know all 4 roots here. And because this is simply x to the power of 4 here, the coefficient of x to the 4 here, that would normally be A. That's 1. What I know then, for each bracket here, so 1, 2, 3, and 4, the x here will simply just be an x in each bracket. We don't need to worry about the coefficient of any of the x's here, so it'll be x, 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 and then finally x again. Okay. So, like we said, we know the 4 roots here. So, for example, this root here, that would be given by x plus 2. If you set that equal to 0, obviously I just subtract 2 off both sides to get x equals minus 2. The next one here, this minus 1, that would be x plus 1. This one here of positive 1, or root of positive 1, that would be x minus 1. And then finally, for this last root here of 3, that would be x minus 3 there. Okay. So all we're going to do here now to find the value of B, C, and D is simply expand these 4 brackets here. Okay. And it's completely up to you on basically the order that you do this and the method you use, whether you use FOIL, whether you use a grid method, anything like that. It's completely up to you. What I'm going to do here though, is I notice these 2 brackets here, that forms the difference of 2 squares. So if I expand those nice and straightforward, that would simply be x squared minus 1. I've got x squared minus 1. Now I've got x plus 2 and x minus 3 there. So now, again, it's up to you how you expand this. What I'm going to do is I'm going to expand these little brackets here, and I'm going to expand the full quadratic with this x squared minus 1. So I've got x squared minus 1. So inside the bracket here, I get x squared. X times x is x squared. I then got x times minus 3, so that's minus 3x. I've got plus 2x, so minus 3x plus 2x, that would give me minus x there. And then 2 times minus 3 would give me minus 6 there. Okay. So from here, I'm going to take these two terms here from the difference of two squares. I'm going to multiply, so for example, the x squared here, I'm going to times that by each term inside the bracket, and I'll do the same with the minus 1 here. Okay, and once you do that and simplify, we've fully expanded, simplified, and then we can identify the value of b, c, and d. Okay, so x squared times x squared, that would give me x to the power of 4. I've then got x squared times minus x, that would give me minus x cubed. Minus x cubed there. We then got x squared times minus 6, that would give me minus 6x squared. That's the x squared done. And I need to do the same here with minus 1. So minus 1 times x squared, that would give me minus x squared. I then got minus 1 times minus x, that would give me positive x there. We get plus x. And then finally, minus 1 times minus 6, that would give me plus 6 there. Really, the key thing to watch out for here is the signs. Obviously, minus 1 times minus x would be positive x. Same again here with the minus 1 and the minus 6 giving you positive 6 there. So it's really easy to make a tiny little mistake there. Just be careful for that. So now we just simplify here, so then we can identify the value of b, c, and d. Well, we simply got x to the power of 4. We can't do anything with that. I've got minus x cubed here. There's no other x cubed term, so it's minus x cubed. I then got minus 6x squared minus x squared. So in that case, simplifying that, that gives me minus 7x squared. We've got the plus x here. Again, nothing we can do with that. So it's just plus x. And then finally, plus 6 there. Okay. So what I've got here now is the quartic expression here. So now we can easily identify the value of b, c, and d. Remember, b is the coefficient of x cubed. So b would be minus 1. So b is equal to minus 1. C in this case, that's the coefficient of x squared, so that would be minus 7. And then finally here, d, well, that would be the coefficient of x, so that would be 1 there. Okay, and there we have it. So that's the solution to B, that's the solution to A, and that gives the solution there to question 7. If we take a look now at question A here, being given figure 4, and figure 4 shows a sketch of the curve y equals f of x, where f of x is equal to 2 times the modulus of x minus 4 minus 3. So for the first part here, part A then, we're asked to find the coordinates of the point Q. We can see the point Q here. That's the vertex of this curve here. Okay. So in other words, it's the minimum point. So how do we find the minimum point here? Well, to begin with, what I'm going to do, just consider y equals the modulus of x. Okay, so I'll quickly sketch that. Won't be perfect. That's going to look something like this. It should actually touch the origin here and go back up. Okay, so my minimum point here is the origin. So it's 0, 0. So from the origin here, we can get to this point here, Q, because y equals f of x is just a series of translations and a stretch here to give us f of x. Okay, starting from y equals the modulus of x. So what do we do here? Well, let's just break f of x down here. So ignore the 2 here. That is a stretch, but it won't affect this point here. So don't worry about that for now. So what I've got here is x minus 4. So the modulus of x minus 4. The modulus of x minus 4. So in this case here, like we said, this is a translation. In this case here, it's 4 units to the right. So we go from 0 here in terms of the x coordinate, and then we go 4 across. Okay, so that's 4 units across. If I give this translation here as a column vector, it would be 4, 0. Okay, so now we put this together with the minus 3. So therefore, if we have y equals modulus of x minus 4 minus 3, then again, this is a translation. So this is a translation here. Again, if I give this a column vector, it would be 4. I've still got the x minus 4 here, or the modulus of x minus 4. We go 4 units to the right. We've already got here. And the minus 3 tells us that we go down 3 units. So it would be minus 3 there. Okay. We will now go down 3 units here to the point Q. And there we can see then that the point Q has coordinates of 4, minus 3. we went 4 units along and down 3. Okay, so from here would be minus 3 there. Okay, so point Q has coordinates of 4, minus 3. Hopefully reasonably straightforward there for the first part. So if I just clear the screen then, let's have a go then at B. So for B now, we're asked to solve the equation 2 times the modulus of x minus 4 minus 3 is equal to x minus 1. Let me just write that down to begin with. Minus 3, and that's all equal to x minus 1. So where do we begin here? Well, to solve this modulus equation, what I'm going to do is just consider the modulus in 2 parts now, the positive solution and the negative solution. If we begin with the positive solution here, that would just give me 2 times x minus 4. We get 2 bracket x minus 4 minus 3 is equal to x minus 1. Okay, so now let's just expand this single bracket here to give me 2x minus 8 minus 3 equal to x minus 1. So we simplify the left hand side here, I get 2x minus 8 minus 3, that gives me minus 11, and that's equal to x minus 1. So in this case here then, if we add 11 to both sides, we get 2x equal to x plus 10, and then finally if I just subtract x off both sides now, we get x on its own is equal to 10. Okay, that's my first solution there, x equals 10. The next solution comes from the negative part here of the modulus, so we take the negative here, I'm going to get minus 2 times x minus 4. Okay, minus 3, and that's all equal to x minus 1. So now again, if we just expand the single bracket here, I get minus 2x plus 8, so just be careful here, minus 2 times minus 4, that gives you positive 8, minus the 3, and that's equal to x minus 1. So from here then, I get minus 2x, got 8 minus 3, so that's plus 5, so plus 5 there, that's equal to x minus 1. Let me just double check we haven't made any mistakes here. So minus 2x plus 5, yeah, x minus 1, perfect. So from here I'm going to add 2x to both sides, so 5 is equal to 3x minus 1, and now if I add 1 to both sides here, we get 3x equals 6, and therefore x equal to 6 divided by 3, give me x equals 2 there. Okay, and there we have it. So that's both solutions there. We solved the equation here, so that's part B done. So finally then, let's just clear the screen here so we can have a go at part C. Now for part C, I'm just going to do this in a different colour here. So for part C then it says, given that f of x equal to p, where p is a constant, has 2 distinct roots, state the set of possible values for p. So what this is saying then, is if we have 2 distinct roots, let me just write this down here. In fact, let me change the colour. Try one more time. There we go, we'll go with blue. If we have 2 distinct roots, what that tells me then is we have 2 points of intersection. Okay, so if we have 2 distinct roots, we have 2 points of intersection. Okay. If you think about this here, f of x equals p is just where p is just a constant. That's just going to be a horizontal line, right? It's just going to be a horizontal line like this. Okay. Now, if it has 2 distinct roots, that means there's 2 points of intersection. So if I just draw an example here, let's say I've got this line here. Okay. I've got that line there. So this is just a horizontal line. So it's of the form f of x equals p, where p is a constant. And we can see the 2 points of intersection here. I've got one here. I've got one here. If I keep going up, we would always have 2 points of intersection. Okay, so keep going up, keep going up. Obviously, we're not restricting the domain here, so we just keep going up. Obviously, this would just keep extending as well. We'd always end up with 2 points of intersection. Okay. Now, where do we basically not get those 2 points of intersection? Well, if you think about it here, this point here, Q, is the minimum point of this curve. So if we're underneath that, we won't have any points of intersection. Okay, so if I'm underneath this here, let's just say we're here. then clearly this horizontal line, again, it's of the form f of x equals p. There's no points of intersection there. We're below the point Q. Now what happens if we're on the point Q? I'll try and draw this, but it probably won't go quite right. Let's just say we're touching Q there, so it's a tangent. We're touching the point Q there as a tangent. We touch the point once. So in that case then, there is not two distinct routes, okay? So to ensure that we have two distinct routes here, we must always be above Q, okay? So therefore, what we can say then is f of x must be strictly greater than -3. Because the y coordinate here, Q, Q has coordinates of 4, -3. If we're always above -3 then, so for example, let's say that's -2 there. We're above -3, so we have 2 points of intersection, -1, 0, 1, 2, 3, and so on. You would always have those 2 points of intersection, okay? But it has to be a strict inequality here, because if I set this as equal as well, then, like we said, that would be this point here where we're tangent to the point Q, and there is 1 point of intersection then. Okay, so it's not two distinct routes, have that one route there, okay? So f of x must be strictly greater than -3, but be very careful here. We need to state the set of possible values for p here. But in that case then, p must be strictly greater than -3. Okay, so any value of p that's strictly greater than -3 would satisfy this condition here, basically of two distinct routes. Okay? And there we have it, so that's the solution to C and the solution to question 8 there. Taking a look now at question 9 here, we've got figure 5 above, which shows a sketch of the curve y equals x, ln x for x being strictly greater than 0. So we're told that the shaded region, labelled as R, is bounded by the curve, the x-axis, and the line x equals 3. And we're asked to show that the area of the shaded region, labelled as R, can be expressed as A ln3 plus b, where A and B are constants to be found. Where do we begin here with question 9? Well, the first thing that I notice here is the equation of this curve, so y equals x ln x, that's expressed as a product of functions. So to integrate this here and find the area, we'll need to use integration by parts. And what I also notice here, we're looking for the area under a curve here. For this total region R, it splits into two parts. I've got this part from here, the origin, to this point here, that's underneath the x-axis, and then from here, this point to 3, that's now above the x-axis. Okay, what I'm going to do here is consider those areas individually, then add those together to get the total shaded region labelled as R. So the first thing that I actually need here would be this point here. Okay, so how do we get that point? Well, everything along this line here is when y equals 0. So x ln x equals 0. So in this case here, we have two solutions. That would be when x equals 0. So that would be the origin here, and we can see that point there. That's the origin O. Then here, well, if x is 1, ln of 1 would be 0. That would also be equal then to 0, because obviously anything times 0 is equal to 0. So therefore, x equals 1 means ln of 1 is equal to 0. Okay, so this point here is when x equals 1. Okay. Like I said, we're going to consider this now in two parts here. So what we're integrating here is x ln x with respect to x. We're doing this now from 0 to 1. That would give me the area underneath the curve here. Obviously, when I find that area, it would be negative because it's underneath the x-axis here. But we'll take the absolute value of that, so it'll become positive. And then we're going to integrate again. X ln x here from 1 to 3. Okay, and again, integrating here with respect to x. So let's start here from 0 to 1. Like I said, we need to use integration by parts here. And the formula for integration by parts is given in the formula book. You don't really have to worry about memorizing this result. So I just give the result here. So IBP for integration by parts. This is given then as the integral of u dv by dx dx. So u dv by dx dx, that is equal to uv minus the integral of v du dx. Obviously then with dx there as well. So what you need to decide here then is what u will be and what dv by dx will be. So in this case here, because this involves the natural logarithm here, so ln of x, what I want to do is I want to choose u as being ln of x because it's much easier to differentiate ln of x than it is to integrate. To actually integrate ln of x, you actually need to use integration by parts. So it doesn't make sense to choose dv by dx as being ln of x. Okay, so therefore, u is equal to ln of x. Then my dv by dx, my v prime here, that would be x then. In this case, the remaining function here, x. So then u prime here, differentiating ln of x with respect to x, that would be 1 over x. And then I want v here, so integrating x now with respect to x, that would be x squared over 2 there. So far that should hopefully be relatively straightforward, just setting up the integration by parts here. So this is where we're probably going to run out of room here now, so let's give this a go. So integrating x, ln x then, with respect to x. I won't be worried about the limits for now. Obviously, once I integrate this, that helps because I can just use the limits individually then. Obviously, I don't need to integrate this again. It's the same expression. So if I just integrate this here, and then we'll worry about the limits. So x, ln x, using integration by parts here, we're going to get uv. So u times v here, so I get x squared over 2 times ln of x. So x squared over 2 times ln of x. And then we've got minus the integral here, minus the integral of v du by dx. So v here, that's x squared over 2. We've got x squared over 2 there, and then we times that by v here, by du by dx even, which is 1 over x, so u prime here, so 1 over x. Okay, that's all with respect to x. What will happen now is this will cancel down quite nicely. So what I'm going to get then, I'm going to get x squared over 2x. Let me just write this down underneath. So I've got the x squared over 2 ln x. That won't change here at the beginning. And I've got minus the integral here. I've got x squared over 2x. So I'll just write it out in full and then I'll just cancel it down. So x squared over 2x. So that x there will cancel one of those x's. So I get minus the integral here of x over 2 with respect to x. So then if you integrate this here, obviously the x squared over 2 ln x won't change. This part here then, if it helps, you can factor the half out using linearity here for integration. If not, you can just integrate as normal. But in this case here, I'm going to get minus x squared over 4. Okay. So now what we need to do here is now consider the limits. Okay. So this is the result that we need here. This is the important part. So take a note of this if you haven't already. So now, if I consider the limits here, we've got x squared over 2 ln x minus x squared over 4. So from 0 to 1 then, remember we start with the upper limit here, substitute that in, and we subtract the lower limit here. I'm going to get 1 squared over 2 times ln of 1. Now remember, ln of 1 is 0, so this part here will just cancel, it'll just be 0. I get minus 1 squared over 4. I'm going to get minus a quarter there. Okay, I get minus a quarter. And then when I substitute in the lower limit here, well, 0 squared over 2, that would be 0 times ln of 0. That will all be 0. Same again here, this would be 0. So I simply get minus 1 over 4 there. Now I need to repeat this here. So x squared over 2 ln of x minus x squared over 4. But this time now, we're going from 1 to 3. So we're now finding the area of this shaded part here. So from 1 to 3. In this case here, there's going to be a little bit more work, but nothing too intense. So if I substitute in 3 here, remember we always start with the upper limit. I'm going to get 3 squared over 2. So that's 9 over 2 there. I then get ln of 3. And I'm going to get minus 3 squared over 4. So minus 9 over 4 there. Okay. Now remember we subtract here the lower limit. So we've already evaluated this lower limit. Remember, that was the upper limit of the first area here, and that was minus a quarter. Now remember, we subtract the lower limit here, so this is now going to be minus a quarter. Okay, so minus a quarter. And I'm running out of room here a little bit. So let me just clear a bit of room here at the top, just so we can finish part, well, not part A off, just the full question, question 9. I should have enough room here if I just clear this top little area here. So let me just finish it off at the top here. So we had x squared over 2 ln x minus x squared over 4. It feels a little bit tedious having to do all this again. But from 1 to 3, like we said, that was 9 over 2 ln 3 minus 9 over 4. And then it was minus a quarter. So that's the same as plus 1 over 4 there. Okay. So minus 9 over 4 plus 1 over 4. That would give me minus 8 over 4, which is minus 2. Okay. So minus 8 over 4. That's the same as minus 2. So this area here is 9 over 2 ln 3 minus 2. So if you think about this in two parts, if I call this R2 here, and this one is R1, then the area for R2, I call this R2 here, that's 9 over 2 ln 3 minus 2. And then R1 here, that was the first one that we evaluated, which was minus 1 over 4. Now obviously, like we said, that was because it's below the x-axis here, so it would be negative. But because we want the area here, we take the absolute value of that. Okay, so that would now become positive 1 over 4. So therefore, for the total shaded region, R is equal to R1 plus R2. What I've got here is 9 over 2 ln 3 minus 2 plus a quarter there. Okay, so minus 2 plus the quarter here. What I'm going to get then, again, you can think about this as minus 8 over 4 plus 1 over 4. That would give me minus 7 over 4. So therefore, R is equal to 9 over 2 ln 3 minus 7 over 4. Okay. And notice now we've got it in the form that we need here. If I just highlight the solution here, this is R. In that case, then it's A ln 3 plus B. So A in this case is 9 over 2 and B is minus 7 over 4 there. Okay, so let's write it down underneath. A is 9 over 2 and B is equal to minus 7 over 4 there. Okay, like you can see here. And there we have it. So that's the solution there to question 9. Taking a look now at question 10 here, so we're told that water is poured into a container at a constant rate of 150 centimeters cubed per second. The container is found to have a hole in the base with the water leaking at a rate of a half V centimeters cubed per second. And we're told here that V centimeters cubed represents the volume of water in the container, and T is the time in seconds. So for the first part here, so for part A then, we want to clearly show that minus 2 dV by dt is equal to V minus 300. So how do we show this here? Well, we just consider how the model actually works here. So what's going into the container? This is the rate of change here now in terms of the volume, which is V. We've got dV by dt, the rate of change here in terms of the volume with respect to time. And in this case here, what's going into the container? Well, that's the water that's being poured into the container at a constant rate of 150 centimeters cubed per second. So that's going to be equal to 150 there. So now we consider what's going out of the container. What's going out of the container here, so again, it would be the rate of change here in terms of the volume with respect to time. So it's dV by dt. In this case here, that's the water leaking. So it's the water leaking at a rate of a half V centimeters cubed per second. So that's going to be minus a half V there. Okay. So what have we got all together here? So we've put everything together in terms of dV by dt. What do we have? So in that case then, the V by dt, that would be equal to 150 minus a half V there. Okay. Now we need to get it into this form here. So at this point here now, we're on the right path, but we need to do a bit of manipulation here, a bit of rearranging just to get it into this form here. So the first thing that I'm going to do here is times through by 2. So I times through by 2, I get 2 dv by dt. That's going to be equal then to 300 minus v. And at this point here now we're pretty close, just one more step to go here. So notice we need minus 2 dv by dt is equal to v minus 300. We've got 2 dv by dt, and then we've got 300 minus v rather than v minus 300. So all I'm going to do here now is just times through by minus 1. In other words, all it will do here is just flip everything. So if it's positive, it becomes negative, and if it's negative, it becomes positive. So I get minus 2 dv by dt. That's going to be equal then to v minus 300. So v minus 300 there as required. Okay. So there we have it. So that's the solution to A. I guess is the first 3 marks there. So let's take a look now at B. And what I'm going to do is I'm just going to clear the screen just because we need basically the full screen here to answer part B. So we're given that there was initially 60 centimeters cubed of water in the container. We want to show that V is equal to 300 minus 240e to the power of minus a half t. So where do we go here? Well, basically what I need to do now is just solve this differential equation here. I notice that we've got this condition here, but this would be my boundary condition for this differential equation, and that allows us to solve it. Okay, so the clue here, because it says there was initially, that tells us that's when t equals 0. When t equals 0, v then is equal to 60. Okay, so what I'm going to do here to solve this differential equation, I need to separate the variables. Okay, so to separate the variables here, you need to make sure that you get this the right way round. So if you struggle to kind of remember or recognize which way the variables would go here, the clue is with the kind of like the numerator and the denominator here for my differential. So dv by dt. So the left hand side here, that would be in terms of dv. So we keep that as the numerator. And then the right hand side here would be for dt. Okay. So because I want v on the left hand side here, dv, I'm going to divide the right hand side here. I'll divide both sides obviously. But I need to get rid of this v here on the right hand side, or this v minus 300. So to do that, I'm going to divide both sides by v minus 300. I'm also going to divide both sides here by minus 2. Okay. So if we do that here, what do we get? Well, I get 1 over v minus 300 dv. So 1 over v minus 300, because we divided both sides here by the v minus 300. So now we get the dv with that. This is just dv on the left hand side. Now on the right hand side here, I'm going to get minus a half then. We get minus a half, and don't forget we need the dt here as well. Okay, so we get minus a half dt. So like we said, dt is on the right hand side. And then from here, what I'm going to do now is integrate both sides. Okay, we integrate both sides here. On the left hand side, we get 1 over v minus 300 dv. That's going to be equal then to the integral here of minus a half dt. Okay, so the left hand side here, that might look a little bit complicated, but remember this is quite a straightforward integral here. So because the derivative here of v minus 300 would be 1, which is the same as my numerator, this would simply be the natural logarithm of my denominator here, so the natural logarithm of v minus 300. And that's going to be equal then, so this is the integral now of minus a half dt. That would give me minus a half t plus c. Get minus a half t plus c there, where c obviously is just our constant of integration. So where do we go from here? Well, we're looking to solve for v here. Okay, so obviously I need to get rid of the natural logarithm here on the left hand side. So we just bring in the exponential function now to get rid of the natural logarithm here. Okay, so e of ln then, that just cancels. They're the inverse of each other, so I get left with v minus 300 on the left hand side. So v minus 300 here on the left hand side. And on the right hand side here then we get e, and this would be my power now. So I get e to the power of minus a half t plus c. Okay, so plus c there. So from here then, what I'm going to do is just put this in terms of V now. So therefore, V is equal to 300 plus e to the power of minus a half t plus c there. Let me just put all that together. Okay, like so. So at this point here now, what we need to do is use our boundary condition. So when t equals 0, v is equal to 60. Okay, so in that case then, v is equal to 60. That's equal then to 300 plus e. Now this power here, minus a half t, well that would be 0, so 0 plus c would just give me e to the power of c then. So plus e to the power of c there. So now I just want this in terms of e to the power of c here. So I'll subtract 300 off both sides. So therefore, I get e to the power of c is equal to 60 minus 300, giving me minus 240 there. Okay, so e to the power of c there is equal to minus 240. Now, at this point here, that might look a little bit confusing because what we need is minus 240 e to the power of minus a half t. Obviously, if I'm saying then that e to the power of c here is minus 240, how does that connect to this power here? Okay, so basically what I'm going to do here now is just use the rules of indices here, or the laws of indices. So if you've got e to the power of minus a half t plus c, that's the same as e to the power of minus a half t times by e to the power of c. Okay, just using our basic rules of indices here. But we know that e to the power of c here is equal to minus 240. I can write this here then as minus 240 e to the power of minus a half t then. Okay, so we go back to v here then, just rewrite this now. What we've got then is v equals, it would be 300. Like we said, this e to the power of minus a half t plus c. If e to c is equal to minus 240, then this part here, e to the power of minus a half t plus c, that's the same as minus 240 e power of minus a half t. So putting all that together then, minus 240 e the power of minus a half t there. Okay, and again, that is as required. So there we have it. So that's the solution there to part B. So finally then, for part C, let me just clear the screen here just so we can have a go at part C. Now it is only 1 mark, but the good news is, even if you couldn't do, for example, part A and part B, you still can have a go at part C. I know it's only 1 mark, but obviously every mark counts, and obviously you just want to have a go at everything that you can. So it says, hence with y state the maximum volume of water that the container can ever hold. So to answer this here, what you need to do is consider the limiting value of v as t tends to infinity. So the limiting value of v as t tends to infinity. Okay, so how does that work here? Well, let's just consider v again. So v is equal to 300 minus 240 e to the power of minus a half t there. So what happens here then is t tends to infinity. So obviously the 300 is just a constant, we can't do anything with that. So what we're considering here then is this minus 240 e to the power of minus a half t. So as t tends to infinity, this part here then will actually tend to 0. Okay, so as t tends to infinity, minus 240 e or minus a half t, this whole part here will tend to 0. And if you're unsure why this actually works, just pick quite a large value here for t. Okay, so if you put this into your calculator, do minus 240 e to the power of minus a half times a really large number. As long as you don't pick too large of a number, you know, basically so it don't give you an error, then what your calculator should return is 0. Okay, so basically as t gets very, very large, this here just becomes 0. Okay, so in that case then, this part here just becomes 0, it just disappears, and I just get left then with v equals 300. Okay, what that's telling me then is the maximum volume of water here that the container can ever hold is 300. So let's just make sure that we get the units here. So the maximum volume, that is equal to 300 And then make sure we get the right units here. Working in centimeters, so it would be centimeters cubed there. Okay, so 300 centimeters cubed. And there we have it. So that's the solution to C. And that gives the solution there to question 10. If we take a look now at question 11 here, we've been given figure 6, which shows a pattern of 4 circles which touch externally, and the center of each circle lies along a straight line of length m units. We can see that line here. And we're told that the radii of the circles form an arithmetic series. The radius of the smallest circle is 9 units, and the value of m is 108 units. So, this radius here, that would be 9 units. We know the value of m here is 108. Okay. So for the first part here, part A, we have to find the common difference for the arithmetic series. So what do we know here? Well, we know the first term, u1, which would simply just be a, that is equal to 9. That's 9 units there for the radius. And we know the sum of the first 4 terms here. And we have to be slightly careful. So I say the sum of the first 4 terms. What we know here is the sum of all the diameters. So this diameter here, plus this diameter, plus this diameter, plus this diameter here. That's equal to 108, okay? If I sum the first 4 terms, that won't be equal to 108 because the sum of the first 4 terms is this radius, plus this radius, plus this radius, plus this radius. You have to be very careful about how you think about this. So what I'm going to do here is divide 108 by 2, so that's in terms of the radius, okay? So therefore, what I know then is the sum of the first 4 terms here would be equal to 54, okay? So we need the formula then for the sum of the first n terms. So Sm would be equal to n over 2 times 2a plus m minus 1 times d. Okay. So if I've got the sum of the first 4 terms then, that would be 4 over 2. So that's going to be 2 times by 2a, where a is 9. So 2 times 9 is 18. And then we have plus, so it would be 4 minus 1, which is 3, times by d, which is what we're looking to solve for. And we know the sum of the first 4 terms here is equal to 54. Okay. So what I'm going to do now is divide both sides here by 2. So obviously you could expand here by the 2, but I feel that's a little bit of a longer way, but it's completely up to you. I'm going to get 18 plus 3d is equal to 27. That's equal to 27. So now subtracting 18 off both sides, we get 3d equal to 9. And then finally, we just want d here, the common difference. We divide by this coefficient here of 3. So d is equal to 9 divided by 3, giving me 3 there. So the common difference for this arithmetic series is simply 3. Okay. So for part B then, it says find the length of the radius for the largest circle. So that would be this circle here. So we're looking for this radius. We're just using the formula then for the m term. We need u4. That would simply be the formula for the m term. Then it would be a. Well, let me just do it in terms of the m term. So un, that is a plus m minus 1 times d. If I want u4, for example, that would be a, which is 9. So let's try and get this correct. So 9 plus m minus 1, so n here is 4, so 4 minus 1 is 3, and we times it by d here, which is 3 as well. So 9 plus 3 times 3, which is 9, we get 9 plus 9, which is 18 there, okay? And if you think about this, you could just kind of continue this pattern here, so increasing by 3 units each time. So this one here would be 12 units, I know that's not quite the center, but that would be 12. This one here would be 15. So clearly 15 plus 3 would give you 18 there. So obviously you could have just extended the pattern there and formed obviously that the radius there was 18 units. But just using the m term then we get 18 as well. Okay, so that's the solution to B. But let's just clear the screen now to have a go at part C then. So for part C then, it tells that another 16 circles are added to the pattern, forming 20 circles in total. We have to determine the new value of m. So obviously we keep adding these circles here. We've got 20 circles in total now, and obviously this line m keeps extending. So how do we determine the new value of m? Well, if you think about this now, m here was double. So m here in this case was 2 lots of S4. Okay, so it was double the sum of the first 4 terms, because the sum of the first 4 terms here was this radius plus this radius plus this radius plus this radius. Okay, if you double that, that gives you that full length there. Okay, so what I need to do now is double S20 because we've got 20 circles in total here. Okay, so you just need to be very careful about how you actually find this length. So M then, like we said, it would be double S20. Okay, let's just remind ourselves of the formula then for the sum of the first n terms. This would be n over 2 times by 2a plus n minus 1 times d. In this case then, we're looking for m, which is 2 lots of S20. 2 lots of S20. So in this case then, S20 would be 20 over 2. I'm going to get 2 times 20 over 2. We times all of this here by 2a. So a is 9 still, don't forget that. So that's 18. And we've got 20 minus 1 times that by d. So 19 times by 3. We evaluate all of this here. 20 over 2 is 10. So if you times that by 2, you get 20. 18 plus 19 times 3. So 19 times 3 is 57. 18 plus 57. And we times this by 20 here. What I get then, so just put all this into your calculator, and what you get here is 1,500. So I'm just going to quickly double check that. So that's what you should get. Let me just double check it. So 18 plus 57 times that by 20. Yeah, perfect. We get 1,500 there. So the new value of m is 1,500. That's part C done. And then for part D here, it says by now splitting up the 20 circles such that no circles touch externally or intersect, find the total circumference of the 20 circles, giving your answer as a multiple of pi. So the reason why it tells you here that the circles are split up such that no circles touch externally or intersect is because we want to just find the circumference for each circle individually. Obviously, we have this point of intersection here where they touch externally. We have to kind of consider what happens there where they're touching. Obviously, they're not touching externally or they don't intersect. We don't need to worry about anything like that. We can just find the individual circumference, sum all of those up, question done. Now, obviously, we have 20 circles here, so there needs to be a quicker way of doing this. We're not going to sit here and find the circumference for 20 individual circles, add all those up. We'll be here for quite a while. So what's the trick here? Well, remember the circumference, C, that is 2 pi r. Okay, so let's just start by finding the circumference of the first 4 circles here and see what happens. So the total circumference then, so for total C, well, for my first one, which has a radius of 9, that would be 2 times by pi times by the radius, which is 9. I'm going to get 18 pi there. So 2 times 9 is 18, times that by pi, you get 18 pi. The circumference of the first circle there is 18 pi. For the next circle then, which has a radius of 12, well, I'm going to get, so let me try it in full. So right underneath, just so you can see the calculation here, this was 2 pi times 9. This then would be 2 pi times 12. That would be 24 pi. This next one here, so my third circle, that would be 2 pi times 15. That would be 30 pi. And hopefully you can see what's kind of going to happen here. Okay. And this would keep going up to the 20th circle. So what would the circumference of the 20th circle be? Well, we need to know the radius then of the 20th circle. So let's find U20 here. I'll do this over here just so I've got enough room. U20 then. So what would U20 be? Well, that would be that would be 9 plus 20 minus 1. That would be 19. And we times that by D here. So that's 3. So 19 times 3, that's 57 plus the 9 there. That gives me 66. Okay. The radius then of the last circle here is 66 units. In that case then, my last one, that's 2 pi times 66. I'm running out of room a little bit here. But in that case then, 2 pi times 66, that would give me 132 pi. But what I know then is the circumference of the last circle is 132 pi. And if you think about this just simply forms an arithmetic series here. My first term is 18 pi. The difference here, the common difference then in this case would be 6 pi. Here we had 6 pi each time, so on and so on, all the way up to 132 pi. But in this case, then I'm simply looking for the sum of the 20 terms here. So S20, but in this case, because we know the first term and the last term, we can use the simplified formula. So this would be now 20 over 2. So let me just write down the actual formula first. So Sn in this case would be n over 2 times a plus l, where l is my last term here. In this case then, S20, that would be 20 over 2, which is 10, times by a, which is 18 pi, plus my last term here, which is 132 pi. Those together. So now 10 times 18 pi plus 132 pi, so that would be 150 pi. So 10 times 150 pi there. Now let me just do the solution over here. Therefore, what we get here for the total circumference is we get 1,500 pi there. Okay, and there we have it. So the answer is a multiple of pi there, 1,500 pi. There we have it. So that's the solution to D, and that gives the solution there to question 11. If we take a look here at question 12, we actually have quite an interesting question. So we're told the stopping distance of a car in an emergency, y meters when driving at a speed of x miles per hour, is given by this general quadratic here. So A, B, and C are just constants. We're also given the following information here that's known about the stopping distance for a particular car. Got the 3 bullet points here. So for the first part here, then part A, we have to determine the values of A, B, and C. So where do we begin here? We're given quite a bit of information, not really any guidance on how we actually find the values of A, B, and C. So we need to be clever about this. But what do we actually know here? Well, the only real information that we know here are these 3 bullet points. So we know that it takes 11 meters to stop when we're driving at a speed of 20 miles per hour. So if you think about this here, x measures the miles per hour that we're traveling at. When x is 20, we know that y is equal to 11 here. When x is now 40 here, we know that y is 33. And then finally, when x is 60 here, the final bullet point, we know that y is 63. Okay, so y is 63. So what can we do with these 3 points here? So x is 20, y is 11, x is 40, y is 33. And then finally, x is 60 and y is 63. Well, what I'm going to do here now is just form some simultaneous equations. Okay, we've got our general quadratic here. I can now form some simultaneous equations. So, for example, we know that y is 11 here when x is 20. So I substitute x equals 20 and y equals 11 into my general quadratic here. What do we get? I'm going to get 11 equal to a times 20 squared. So it would be a times 400. So let me try it out in full. So a times 20 squared. Then we've got bx, so b times x here, which is 20. And then finally we've got c here. Okay, so that would be my first equation there. We can now repeat this again 2 more times. So when x is 40 here, y is 33. So 33, so a times 40 squared plus b times 40. And finally again we get plus c. And then one more time here, y is 63. I get a times 60 squared plus b times 60, and then plus c. Okay, if I simplify these 3 simultaneous equations here, what am I actually going to get here? Well, I get 11 is equal to 400a plus 20b plus c. Let's call that here equation 1. For my second equation here, I get 33. That would be equal now to 1600a. I then get 40b plus c, so that's equation 2. And then finally for equation 3 here, this bottom equation, I get 63. That's going to be 3600a plus 60b plus c, and that's my third equation. Okay, so what I need to do now is solve these equations here. Okay, and what I'm actually going to do here now is rearrange equation 1 so that c is the subject here. And what I can do then is substitute that into equation 2 and equation 3, and then in that case then it would just be in terms of a and b only. Okay, and from there we can solve simultaneous equations like we normally would. So Like we said, let's rearrange equation 1 now. So new equation 1. So making C the subject here, I get C is equal to 11 minus 400A minus 20B. Like we said, now what I'm going to do here is substitute C now into equation 2 and equation 3. Okay, so we have 33 is equal to 1600A plus 40B, and we've got C here. So let's just write it down in full. Plus 40B plus C here, so that's going to be plus 11 minus 400A minus 20B. I'm now going to do the same here for equation 3 here. I'm going to get 63. That's going to be equal to 3600A plus 60B and then C. So let's just write it down in full. I can see there is a lot of writing for this question here. So plus 60B plus C then. So again, that's 11 minus 400A minus 20B. So now if we simplify all of this here, so let's call this then equation 4 and equation 5. My new equation 4 then, when I simplify all this then, I'm going to get 22. So 33 minus 11, that gives me 22. I've got 1600A minus 400A, so that's 1200A. Get 1200A there. I've got 40B minus 20B, so that would give me plus 20B there. So that's my new equation 4 there. We'll call that 4 star. That's my new equation 4. Doing the same now here for equation 5 to obtain new equation 5 here. So I've got 63 minus the 11 here. So that would give me 52. That's going to be equal then to, what have we got here? We've got 3600A minus 400A, so that's 3200. I've then got 60B minus 20B, so that would be plus 40B there. Okay, and that's my new equation 5. So we're getting closer here, but we're not quite done. What I need to do now is solve these simultaneous equations here. And obviously it's up to you which way you actually go about this, but I think just using elimination here is pretty straightforward. All I need to do then is just times this top equation here by 2, so I can match the coefficients here for B. So I'm going to times this equation now by 2. Okay, so if I times this by 2 underneath here, what am I going to get then? Well, 22 times by 2 is 44. We get 44 there. 1200A times by 2, that's 2400A. And then we've got 20B times that by 2, that gives me the 40B, and that's perfect. That's what we need. We need those coefficients to be matching. So perfect. And from here now, what we can do is we can now solve these simultaneous equations like normal. So we're going to subtract here to eliminate the B's. We subtract. So in this case, 52 minus 44, that would give me 8 there. Get 8 there. I've then got 3200A minus 2400A, so that would give me 800A there. Then obviously 40B minus 40B, they just cancel. In that case, then we've got 800A is equal to 8. So therefore, A is equal to 8 over 800. Which gives me 1 over 100 there. Okay, we find the value of A there, so therefore A is equal to 1 over 100. We now need the value of B here and the value of C. So for the value of B then, all I need to do is simply substitute this back into either of these equations here. And again, it's completely up to you which of these equations you substitute into. If I substitute that into equation 5 here, so to find B, we don't have much room here, so let's do it up here. So to find B, I'm going to substitute A equals 1 over 100 into this equation here. So we've got 52 is equal to 3200 times 1 over 100. Then we've got 40B. So 3200 times 1 over 100. So what would that give me here? It's actually going to be 32, right? So 3200 times 1 over 100. Yeah, that gives me 32. So I've got 52. I kind of run out of room here. Do it over here. So 52 is equal to 32 plus 40b. In this case then, subtract 32 off both sides, I get 40b is equal to 20, so therefore b is equal to 20 over 40, giving me a half there. Okay, the value of b here is a half. And we're nearly there now. Just need the value of c then to finish with here for part A. So in that case then, I can simply use this rearranged form here for c, nice and straightforward. So do this in a different colour just to highlight this. So therefore c here is 11 minus 400a, so that's minus 400 times 1 over 100 here. We don't have much room at all for this question. And then minus 20 times b, which is a half. Just quickly do that on my calculator, just make sure I get all this correct. So 400 times 1 over 100, that would give me 4. Minus the 20 times a half there, so that's minus 10. I get 11 minus 6 there, and that gives me, something's not gone quite right there. Let's double check this. So 11, do this over here. Have I got room? I don't have much room. Let me just scribble these two out underneath, just so I've got enough room here. Because we don't have loads of room. I think it actually might be correct. Let me just double check this. I'll be upset we've done all this work and it's incorrect. So c is equal to 11 minus 4 minus 10 there. So 11 minus the 4 minus the 10 there. Ah, perfect. It gives me minus 3. That's what we needed. Perfect. Good stuff. So c is equal to minus 3 there. And there we have it. So that's the value of a, b, and c. So I guess the first 6 marks there. Quite a lot of work really just for those 6 marks. So let's just clear the screen then. And let's take a look then at b here. So hopefully you've got the values of a, b, and c still, because we do need those. So a, 1 over 100. B is a half. And c is minus 3 then. Okay. If we put that all together, I've got y equals 1 over 100 x squared. I've got plus bx, so plus a half x. And then finally, plus c, which is minus 3. Now for part B then, we're given that a car has a stopping distance of 21 meters. We want to find the speed of the car. What we know here then is that y is equal to 21. Okay. I've got 1 over 100 x squared plus a half x plus a half x minus 3, and that's all equal there to 21. Okay, so that's the stopping distance that we're told here. So in this case here, what I'm going to do is I'm going to set this quadratic equal to 0 now. So I subtract 21 off both sides, I get 1 over 100 x squared. Obviously you could write that as 0.01 as well if you prefer, plus a half x. And then minus 3 minus 21 gives me minus 24 there. And that's all equal to 0. So from here now, there's a few different ways that you can solve this quadratic here. It's completely up to you which method you take to solve this quadratic. So obviously I could complete the square here. That's one way I could do this. I could use the quadratic formula. That's another method. Or what I could try and do is see if I could factorize this. So in this case here, if I times through by 100, what would I get? Well, what I'm going to get here then is x squared. Well, half times 100 there, that would give me 50. So I get plus 50x. And then I get minus 2,400. And that's equal to 0 there. Okay. And if I just double check this now, whether this factorizes, you can use the function on your calculator. If your calculator can factorize something like this, you will find your solution. That is one way to do it. If you just factorize this here, I'll get double brackets, like so. Obviously, I'm going to get an x at the front of both of these brackets here, like so. So two numbers now that would times give me minus 2,400. So I'm going to take 80 and minus 30 here. So I get x plus 80 and x minus 30 there. Okay. So clearly the issue here is I get two solutions. We're just looking for the singular speed here. Now clearly one of these solutions would be negative. So this x plus 80 here, that tells me that x is minus 80. Now clearly the speed here should be positive. So it can't be that solution there. in this case then x is equal to 30. Okay, the speed then is 30 miles per hour. Okay, and there we have it. So 30 miles per hour, draw it out in full. 30 miles per hour there. Okay, and there we have it. So quite a lot of work for that question, but hopefully you found that a bit of an interesting question, a little bit different. So 6 marks there for finding the values of A, B, and C, and the final 2 marks there for finding the speed of the car with a stopping distance of 21 meters. So there we have it. So that's the solution there to question 12. And finally then, if we take a look here at the very last question on this paper, question 13, we've got the movement of a bird as it flies above ground, and this is recorded. So the height h meters above ground level is modelled by this equation here. So t is the time measured in seconds from when the bird passes over a checkpoint. So for the first part here, part A, we're asked to express 3 cos t plus 4 sin t in this harmonic form here. We want to give the exact value of r and the value of alpha to 1 decimal place. I think the first part here, part A, is pretty standard. Nothing really to kind of trick you up here. Remember to find r. So to find r here, this is a simple application of Pythagoras. This would be the square root then. And remember what we do now is we square the coefficients here of the cosine function and the sine function. So it would be 3 squared plus 4 squared. I get 3 squared plus 4 squared. And notice here what this is a Pythagorean triple. So this is the square root of 25. As a result, then we get an integer here. This is equal to 5. And now we need the value of alpha here. So to find alpha, this is now tan inverse or arctan, whichever you prefer, tan inverse or arctan, absolutely fine. So we need tan inverse here. Let me just write down that this is for alpha as well. So in this case, it would be tan inverse. It would be the coefficient here of the sine function. So it would be 4 divided by the coefficient here of the cosine function, which is 3. I'm taking tan inverse here of 4 over 3. Obviously, do ensure that your calculator here is in degrees mode rather than radians. It's usually people making the mistake the other way around, but obviously you need to be working in degrees mode here. So in this case here then, what I get, obviously making sure that you give this to 1 decimal place, I get 53.1. Okay, so the value of alpha there is 53.1. Now, we're not done here. What I want to actually do is just express this now in this form here. So make sure you actually do that to finish off here. So I've got 3 cos t plus 4 sin t. We've got 3 cos t plus 4 sin t. We can express this in this form then. So r is 5. I get 5 cos, and I get t minus alpha. So that's going to be t minus alpha here, which is 53.1. Okay, and there we have it. So that's part A done. Like I said, hopefully nice, straightforward there, pretty standard. Nothing really to kind of trip us up there. So that's the first 3 marks. Now let's take a look here at B. So in B it says find the height above ground level when the bird passes over the checkpoint. If you think about this here, it's just 1 mark, so kind of use that as a guide. Shouldn't really be too much work here. And the reason for that is because that's the initial point here. So when t equals 0, we're looking for the height here. Okay, so it passes over the checkpoint when t equals 0. So in this case here, just using the original equation then, we know that h is equal to 600 divided by 18 plus 3 cos 0. So 3 cos 0 plus 4 sin 0. So in this case here then, I'm going to get 600. This would be divided then by 18. Remember, cos of 0, that is 1. So I get 3 times 1 there, so plus 3. And then sine of 0 is 0. So 4 times 0 is obviously just 0. Get plus 0 there. Obviously, you don't have to include the plus 0, but just to show you what actually happens. Obviously, then I get 600 over 21 there. Okay, so 600 over 21. So in that case then, you could give your answer like that in its exact form. But if you do want to give it to, say, 1 decimal place, this would be 28.6. Get 28.6 meters there. Okay, so that's the initial height of ground level when the bird passes over the checkpoint. That's part B done. Now for part C here, 3 marks for this, and we do need a bit of room, so let me just clear the screen to begin with. So for part C then, It says find the minimum height of the bird above ground level and state the value of t for which this occurs. So let's just take this equation here. What I'm going to do is replace this 3 cos t and this 4 sin t with the harmonic form that we found in part A. So what I get then is 600. That's going to be all over 18. We've got 5 cos t minus 53.1. Okay. So just replacing now this 3 cos t plus 4 sin t with the harmonic form that we found in part A. Obviously, we want to use that part, or use this part here in part A, something actually useful, so that's where we're going to use it now. So, how do we find now the minimum height of the bird above ground level? Well, what I need to do then, if you think about this fraction here, I need to maximize the denominator here. Okay, make this as large as possible. So how do I actually maximize the denominator here? So maximize the denominator. Let's just write this down just so it's clear what we're doing here. Maximize the denominator. So in this case then, what I'm going to do is consider how I make this as large as possible. And it's obviously going to have something to do with this 5 cos t minus 53.1. I can't do anything with that 18, that's just a constant, so I can't do anything with that. But for the 5 cos t minus 53.1, we can actually do something with this to maximize this. And in this case, I just think about how I actually maximize this here. Well, that would be when cos, so this is when cos or cosine of t minus 53.1 is equal to 1. Okay, so the maximum of cosine is equal to 1. Okay, so in that case then, the maximum here of this cosine would simply be 1. I'm going to get 18 plus 5 times 1. So therefore, the minimum height here would be h is equal to 600 divided by 18 plus 5 times 1. Essentially, it's just your value of r here. Okay, so 5 times 1, because this is maximized, or it is maximized when cosine of t minus 53.1 is equal to 1. So again, if I just give this an exact form, I'm going to get 600 over 18 plus 5, so that would be 23. So again, you could leave it in exact form like that, but again, if you do want to give this to, say, 1 decimal place, this would be 26.1. I get 26.1 meters there. Okay, so that's the minimum height of the bird above ground level. But we're not done here because we also need to state the value of t for which this occurs. So think about how we maximize this denominator now. That was when cos of t minus 53.1 was equal to 1. But in that case, I need to find here cos of 0. Okay, cosine of 0. Well, to get cosine of 0 here, that would be when t is equal to 53.1. So therefore, that is when t is equal to 53.1 there. Okay, so you don't really have to think too much about that. Or I should say there's nothing mathematically too challenging for part C there. But just thinking about how we actually maximize the denominator there, get the minimum value or the minimum height for the bird. Okay, that's the solution to C. So we're nearly done now. Let's just clear the screen one more time here to have a go at part D. So for part D then, it says find the value of t for when the bird is 30 meters above the ground. So again, I'm going to take this model here for the height of ground level. So h is equal. But again, what I'm going to do is replace my 3 cos t plus 4 sin t with the harmonic form. So h is equal to 600. That would be over 18 plus 5 cos of t minus, is it 53.1? Yeah, 53.1. Okay. So if we're looking for the value of t for when the bird is 30 meters above the ground, what I'm going to do now is set the height here, h, as 30. So 30 is equal to 600 all over 18 plus 5 cos t minus 53.1. Okay. So all I need to do now is solve for t here. That will give me the value of t. And there's a few different ways you can get it into the required form here. The way I'm going to do it is probably not the most elegant, you know, with the most finesse, for example. All I'm going to do here is just times both sides by 18 plus 5 cos t minus 53.1. I get 30 lots of my denominator here, so 18 plus 5 cos t minus 53.1. And that would be equal then to 600. Okay. So I suppose in this case, the other way you could do this would be to divide through by 30. So let's just do that here just to save a bit of time. If I divide through by 30 here, 600 divided by 30, that should give me 20. Yeah, perfect. So I get 18 plus 5 cos t minus 53.1 is equal to 20. When I originally did this, I expanded this bracket here, which is fine, but it's quite a long way of doing it. So this is definitely the quicker way. I'm not quite sure why I didn't do this the original way when I did this question. So what I'm going to do now is obviously solve for t here. So I'm going to subtract 18 off both sides. I get 5 cos t minus 53.1. That is equal to 20 minus 18, so that's equal to 2. And now if we divide by this coefficient here of 5, that cosine of t minus 53.1 is equal to 2/5. Okay, and we're nearly done here now. All I need to do now is take the cosine inverse or inverse cosine of both sides here. So in that case, then I get left with t minus 53.1 is equal to cos inverse 2/5. So cos inverse of 2/5, let me just quickly do that. Obviously just make sure that you are in degrees again, not radians. So what I get here is 66.4218 and so on. Obviously we just want t here, so don't forget we also need to add 53.1 to both sides here. Therefore t is equal, if you add 53.1 to this, and it doesn't ask us to give it to a specific degree of accuracy here. So if I just give it to one decimal place, that should be fine. What I want to get here then is t is equal to 119.5 there. Okay, you should get 119.5. So all I've done there is took cosine inverse of 2/5. That gives you 66.42182152 and so on. And then add 53.1 to both sides. And I've just rendered that to one decimal place. Okay, so that's to one decimal place there. Okay. And there we have it. So that's the solution to D. That is the solution there to question 13. And that actually brings the end of this paper here. So this was paper 2 for set A. I hope you have found this helpful. Like I said, if you are one of the 2023 students who's using this almost like a predicted paper, like I said, hopefully you find this helpful. Like I said, the topics won't match up perfectly, but it should still be a pretty good guide and give you some good practice before the upcoming exams next week, and obviously the applied paper as well in a couple of weeks. So I'll be doing a paper 3 as well. Keep an eye open for that. That will be coming out shortly as well. Other than that though, I think that covers pretty much everything. If you're looking for extra A-level maths revision such as worksheets, revision videos, and basically where all my predicted papers are, go and check out AJMaths.co.uk. Best of luck with paper 2 next week and paper 3 as well in the upcoming weeks. So yeah, cheers guys.